So let's try and see if we can understand some of the new observations on these materials in light of understanding the TADF mechanism in this picture of the coupling. So the first thing is that because we're coupling two independent states, we can play around with those states independently. So I can tune the CT state with the environment without affecting the local triplet. Okay? So, we have a lovely name for this compound. We call it super blue. Right? This is super blue. So it's the acridine donor with a twisted SS dioxide acceptor. We got that material, we put it into MCH, and you get an energy gap of about 150 millielectron volts. Right? So not wonderful, but you get delayed emission, and it fulfills all the normal criterion for TADF, but it's just got a big gap. But it emits in the blue. This is the time-dependent measurement of the intensity, and you can see that you get very strong thermal activation of the DF, right? When you're in this non-polar environment. We then said, well, we're going to make a device, what we're going to put it in, so we thought we'll put it in DPEPO host. Turns out DPEPO is a little bit polar. We put it in DPEPO, and we shift down the CT emission by 150 millielectron volts. He says, smiling, because now the energy gap is around 50 millielectron volts or less. Now look at the temperature-dependent emission. So you can see that the DF starts much higher intensity and earlier in time, and even at 80 Kelvin, it's almost all DF. And it's no phosphorescence, so the actual thermal activation is much weaker because the gap is so much smaller. Okay? And we get a lot more DF because the gap has closed right up by this tuning. More interestingly, the PL quantum yield in DPEPO, oh, I left one E in, damn, is 95%. In ZNX, it was 30%. And in DPEPO, which does have fairly good oxygen permeability, right, the oxygen doesn't quench the DF. The DF is so fast, it's faster than oxygen quenching. So the oxygen experiment is not a completely good test for TADF. The TADF is really fast, you won't quench it. In this case, it's about 3 microseconds, a little bit faster.
It depends on the host.
Yeah, but that's why I said it's in DPEPO, right? In DPEPO, it's got to be fairly slow.
No, therefore, this might be the reason.
Yeah, no, that's what I said. It's exactly the reason. The TADF process is faster than the oxygen permeability. That's all it's telling you. Yeah? Okay. But, so we now have this molecule. We've tuned the CT to be resonant with the local triplet, and it's much more strongly TADF. Right? So if you look at, that's the electroluminescent spectrum and the phosphorescent spectrum overlaid. And if you look at the onset, they're right on top of each other. Right? The only reason that the electroluminescence is canted over a little bit, which we found out a little bit later, is that we were getting an eczema with, an ectiplex with the TPBI. And you have to put in a blank layer of DPEPO in here to stop it forming an ectiplex, but that's why it's not quite completely on top. But the gap is less than 5 millielectron volts, and we get a, I thought I took that one out, I'll skip that one. So for the super blue, now you know why we call it super blue, we get an EQE of 22%. So the PLQI has got to be around 100, and we're harvesting almost every triplet in this material. But the only way we've achieved that is by tuning the CT to be in resonance with the local triplet. If you don't do that, the device is useless. Okay? So we can start to see how important this resonance between those two states are. So let's do something fairly trivial on the face of it. Right? So this is 2K, and this is what we call the linear isomer of 2K. Now, to a physicist, there is no difference in those two molecules whatsoever. All right? I have to look very hard to even see the difference, but I'm a physicist. All right? The chemist convinced me, yeah, it's different. Look, it's really different. Okay? So, yeah, it's different, you know. They then did the calculations, and they said, oh, there's something strange going on here. Okay? If you look at the linear material, right, the two donors are in different conformations. They're always perpendicular, but there are two ways to be perpendicular. So one is called the equatorial and one is called the axial. And in the linear 2K, right, there's a possibility that you could have this mixed equatorial and axial conformation, whereas in the bent 2K, right, I'm a physicist, I call it bent. Sorry, it's meta and para, but it's bent and linear to me. Right? It's always equatorial. So we wondered what you were going to get when you actually made the material, and luckily, the linear is this equatorial axial conformation. So I have the molecule now where I've got the donor. The two donors are different. They're in different conformations. Same donor, different conformations. In normal 2K, it's equatorial, equatorial. So we thought, all right, let's have a look to see what the difference in the physics due to that, to me, minor little difference. Mm-hmm. So the reason that you get these two conformers comes from the fact that you can have two conformations of the phenothiazine. Because the 3-phenyl ring system in the phenothiazine is bent, you can have the hydrogen from the nitrogen kind of pointing inside the bend or outside of the bend, and you call it H intra and H extra. And that subtle conformational difference gets taken over into the DAD molecule. So you end up with this quasi-equatorial and quasi-axial conformation of the donor acceptor coming from the phenothiazine. So this whole effect is really dominated by the actual structure of the donor, phenothiazine. In things like phenoxazine, which is virtually flat, you don't see the difference. It's phenothiazine because it's like a banana that we get these differences. Okay? So let's have a look. We'll do the simple things first. So we look at absorption and emission. So the 2K, which has now become MA. Sorry about we changed the nomenclature, but we weren't allowed to use 2K in the paper. So we called it MA, which is the bent, the normal 2K, and MB is the linear. Okay? So you can see now the absorption spectrum of MA is a simple linear combination of the donor acceptor, like we've seen before. But when you look at the MB, the one which is now linear, but we also now know is equatorial axial, you can see that the oscillator strength has been pushed down to lower energy. That's the yellow one. So the mixing of the M pi and the pi pi states is different. And that's because the para-coupled one is more conjugated. We think the pi orbitals are getting pushed further via the H intra bonding across the donor and acceptor, so it's more conjugated, right? So you get a higher extinction coefficient down here. And in fact, Tom calculated the oscillator strength, and the oscillator strength of the linear is twice as high as the oscillator strength of the bent because of this extra conjugation. So the difference between, if you like, para and meta is a little bit of conjugation between the donor and acceptor. So it increases the oscillator strength, which you would have thought would be good because it should increase the radiative decay rate. Right? Not quite. You can also see that the CT state, the CT emission of the linear, MB, is at lower energy than the 2K. So the yellow is at slightly lower energy than the green. But if you look at the shift from the band edge to the emission, the CT is shifted further from the absorption band edge in MA than it is in MB. All right? So in the bent one, you get effectively a bigger Stokes shift than in the linear one, which is a bit strange, but you can see that from the spectra. The more important thing is that when you look at the emission, so when you know the emission of 2K, you get one nice strong CT band, and it shifts to lower energy in higher polarity. The MB has two CT emissions, one at low energy and one at high energy. They both blue shift. Sorry, they both red shift with polarity. They're both CT states. If I go to acetonitrile, right, the emission from what I'm going to call the equatorial CT state has shifted so far to the red you don't see it. But the CT state of the axial CT is still there. It's the yellow one. Right? So in this linear CT molecule where you've got one axial and one equatorial donor, you get two different CT states of different energies, depending if it's an equatorial CT, which is low energy, or the axial CT, which is higher energy, and you actually see dual CT emission from the one molecule. So it tells you that the two conformations are stable with respect to each other. And you don't energy transfer between the high energy one and the low energy one, because you can see both at the same time. Now, if you've got energy transfer from the axial CT to the equatorial CT, you'd never see the axial CT emission. But you see both. So on that one molecule, all three components are orthogonal to each other. The two donors are orthogonal to each other, and they're both orthogonal to the acceptor.
The conformation of the compound is the same, and it's not changing.
It doesn't seem to. I will show you later on when we can make something change, but no, basically they're still there because I get these two distinct CT states. They're both CT states because they both shift with polarity. Yeah? Hartmut?
Molecules sit in a matrix, right?
This is in solution. This is stable in solution, so even in solution they're not moving. They're fixed in those two conformations. So the two conformations are local minima, obviously.
These two conformations in the NMR, the two different components.
Can't remember. I had to ask Jonathan. No, I can't remember. I would have thought we had to, because we see it in emission. Yeah. I have to go and check. I don't know. Try and find out. All right, so, yeah? Yes, because this is the electrochemistry. And you can see the redox coupled's almost identical, right? The reduction's the same, but the oxidation is shifted just a little bit, okay, between the MA and the MB. So I think they're going to have separate frontier orbitals for each one, yeah? So this is electrochemistry, and the only difference in electrochemistry between the linear and the bent is just in the oxidation wave. So the LUMO is different. Get it right, yeah? So let's have a look at a little bit more closely at the electronics of the system. So this is 2K MA, right? And that's looking on the band edge again to see this very weak N-pi transition right on the band edge in the 2K molecules. We've seen that before, yeah? In the linear version, where you've got equatorial axial, you can see that it's virtually gone. So that change of the structure from the bent to the linear has changed the conjugation, especially through the axial conformation, and you've mixed the states in a different fashion. So the mixing of the N-pi and the pi is different in the two molecules, right, because of the conformation. So this one has got a much weaker direct CT transition than that one. Okay. So it looks subtle, but it has effects. This is Tom's, right? You like I just noticed what you did.
No, this is purely because I was always told this is best for people with colourblind.
All right. So those that have been in the laser lab in Durham know that it's painted in these colours. I thought you chose the colours to match the laser labs. But anyway, if you look at the orbitals of 2K and the linear, all right, you can see that at the lowest energy is on this axial. So the modelling is difficult because now we know that we actually can have both states at once. And is that DFT or time-dependent DFT? That's DFT. So DFT can't cope with this molecule. It's too complicated, all right? Because we know that there are both states there. But anyway, you can talk to Tom about that. But the important thing is, and this is coming back to this conjugation and mixing of the different pi and n orbitals. So in 2K, you remember this is Fernando's experiment, that as you go and excite right down on the band edge, then the quantum yield goes up. Okay? So this is, in green is the 2K, you excite right on the very band edge, you get the direct CT absorption, and the quantum yield goes up. That doesn't happen in the linear version. You go on the band edge and it doesn't increase. So by changing the mixing of the n-pi star and the pi-pi star, you're changing the transitions that you can get, and you can't get this direct CT transition in the linear version. Right? So there's more difference coming out from the conformations on these molecules. The oxygen dependence starts to get even more complicated. But if you look at the linear one, when you look at the spectrum with oxygen, you can just see the two CT states, the two prompt CT emission from the two CT states. So it's that one there. So this is the axial CT and that's the equatorial CT. In the normal 2K, you only see the equatorial. Okay? So you can pick them out, you can see that they're stable in there. And in solid state, you can really see the difference in the absorption spectrum in Z and X. So the linear version is very, very different, has much higher oscillator strength down here than the normal 2K. So just changing that conformation of the molecule is really changing everything in the system. Right? So if you think you can make a DAD molecule and you can bond it any way you like, you're going to get changes. And the changes are subtle, but they have big effects on the TADF performance. Because when you look at the triplet states of those two molecules, so in green is the phosphorescence of 2K. Right? You've seen that before, and we know that that phosphorescence is a mixture of donor and acceptor phosphorescence, the two dual phosphorescences. In the MB molecule, the linear one, you only get the donor phosphorescence. Right? So there's no coupling between the triplet states. Whereas in 2K, there's coupling between the two triplet states. So that's why they both coexist. And Tom has calculated the coupling strength between those two triplets. I haven't talked about photoinduced absorption, but in the photoinduced absorption experiment, we can actually see, we can pull out the triplet absorption of the axial as well. So we can really see that it's the actual axial conformation is there with the equatorial conformation, and I can see the excited states of both conformations at in the same experiment. Okay. So now we look at this triplet, all right, and we think, where is the triplet of the axial state? So this is a complicated diagram. This is 2K, and you know what 2K does between MCH and toluene, right? So that's this one. So this is just what happens when you tune the CT band in 2K in toluene and you push it further away from the triplet state. That's simple because it's equatorial. In the axial, in the linear version, okay, you've got the axial conformation, and equatorial conformation. Can I borrow your teeth, please? I think mine are coming out. And the triplet state of the axial conformation is actually lower energy than the triplet state of the equatorial. It's because the axial state is a much weaker CT state. So it has a much bigger exchange energy. And the triplet state of the axial is actually lowest. Right? So you can't have coupling between the axial local triplet and its CT state. So the axial part can't give you TADF. Only the equatorial part can give you TADF. Now, to show you that in more detail, I'm going to skip a few. What time's Pete?
Now, 18 minutes.
Before coffee? That's all right. Let me skip. It's decided not to go. Come on. Right. Okay, so I want to get to the second molecule. So before we talk about this effect of these different triplet states of the axial, just to show you what happens when I take that linear material in a device, it's much, much worse than the 2K. Right? The turn-on voltage and everything is identical, but the roll-off is much stronger and the performance is much worse. That's because the axial triplet state is now acting as a trap. Yeah? And the axial triplet cannot couple to the equatorial CT state. So by having those two conformations, we've suddenly built in a trap. The axial conformation is bad. In 2K we're fine, it's not there, but in the linear one, when the axial conformation is stabilized, it's much, much worse. All right? What we're learning is that these states don't couple, so there's no energy transfer between the high energy axial CT and the low energy equatorial CT. They don't talk to each other. The triplets don't talk to each other, but they still exist, and so the axial forms a trap. Right? Now, let's go to the last molecule, where we now we hang off this little CH3 group on the donor. By doing that, we end up with the conformation which is axial-axial. So we can now compare a molecule which is equatorial-equatorial with a molecule which is axial-axial. Same donor, same acceptor, apart from that little CH3 group on the top. Okay? So the CH3 group shouldn't really change the electronic properties very much at all. All it's changing is the conformation. All right? So let's now compare the pure axial with the pure equatorial. So first off, you look at the absorption spectrum. Okay? The absorption spectrum of the axial-axial is completely different to the absorption spectrum of the equatorial-equatorial. So you can see all the oscillator strength has been pushed right back into the pi stars, so the n-pi stars kind of disappeared. And the extinction coefficient is twice as strong for the axial. Okay, so you've lost the band edge, but you've increased the oscillator strength in the main pi. Okay. Yep. If I look at the emission, so this is equatorial on the left. Right, so that behaves itself like we've seen before. It starts off in MCH, it's already CT, and as you put it into more polar environment, the CT just shifts. We think this is donor emission down here. Okay. So this one behaves itself. You've seen this before, we know what this is doing. We now look at the axial-axial. Right? So this gets complicated. So as a reference point, the black spectrum in there is the donor. And you can see that in non-polar environment, you actually get an emission band above the donor. So the axial CT state is actually at higher energy than the donor emission. As you put it into more polar environment, you suddenly get this equatorial emission built in. So you take this axial-axial molecule, you put it in strong polar environment, it flips, or one of them flips to being equatorial, and there's the equatorial band. Right? So you can change the conformation by putting it in more polar environment. Even more interesting is if you change where you excite the molecule, so you give it a bit of excess energy. You excite deeper in the UV, you also get equatorial formed, and you get equatorial emission. So you can drive this change in conformation with excess energy, or you can change it with the polar environment, or maybe you excite it and it stabilizes. Right? So this axial-axial is really complicated. But what you can say is that it's converting. Now when we looked at the equatorial axial, they were stable. You could see both the axial and the equatorial at the same time. But when we've got axial-axial, one of them wants to form an equatorial. And there's two ways of stabilizing that. Polarity or excess energy. Okay? And I've got Crystal to thank for the idea of excess energy, because in one of your papers you talk about excess energy and playing around with mixing of states and things. That's what it does on this molecule. Okay. So to look at that, this is the axial material. And what Paloma did was to look at the contribution of the axial CT component and then the equatorial CT component as she increased the excitation energy. And you can see it, when you hit on the band edge, you get predominantly the axial high energy CT. As soon as you reach a little bit into the absorption band, the red dots, you suddenly switch on the equatorial. So you can see that you need a little bit of excess energy to suddenly switch from mostly axial CT to having something which is equatorial CT with a bit of axial. And that's in the same polarity. Okay. This is just now comparing the time resolved emission of the equatorial, which behaves itself normally. You get this nice, strongly thermally activated delayed fluorescence component. With the axial, there is no delayed fluorescence until you get into DCM, where the polarity is high enough. You start to see the equatorial CT emission, and bingo, you get the delayed fluorescence come back. So the delayed fluorescence is only coming from the equatorial conformer, not from the axial. Right? The simple reason is that the triplet of the axial is so far away from the CT, there's no coupling, there's no TADF anymore. There's no reverse intersystem crossing anymore. Okay. If we look at the emission band at different times, so on here again we've got the equatorial. So you can see at very early time we get a little bit of donor emission because we're exciting the donor, and then we get CT emission all the way through into the microsecond. If I look at the axial, this one, right, you see that we get a very strong axial emission which decays very quickly. The lifetime of the axial is very fast. We get perhaps a tiny bit of equatorial, and then very quickly we're into phosphorescence. Right? So by 1 microsecond, you've just got phosphorescence in this axial conformation. Right? And the best that we've managed to measure so far, we think the lifetime of the axial CT state is less than 3 picoseconds. Single photon counting isn't resolving the lifetime of that axial component. It's really quick. But I think probably that's because it's just getting quenched, the triplet, so fast that there's virtually no lifetime for the singlet CT to emit. It's just gone. Yeah? So there is another process. So when the gap between the CT and the triplet is big, in this axial conformation, there's still a fast intersystem crossing. I don't understand that, unless this quenching is completely something else. Right? So we don't understand that part of the photophysics yet, but it's hard to measure. In ZNX, we look at the axial, and what we find is it's much harder to get the axial conformation to turn to the equatorial conformation when you've got it in the solid matrix, right? Which stands to reason. It's got to have a physical movement from something like this conformation to this conformation. Put it in solid, it can't do it. So we think this is telling us, so when we look at the time resolved emission, you see the axial conformation is living much longer. So there's a real physical flip that's going on somehow. Yeah? This is, okay, that's the equatorial in ZNX, and it behaves itself. The gap is not so big, and so we get a fairly nice thermally activated component. Okay? So basically, the conformation is controlling everything that we see in these systems. When we look at the axial in ZNX, Right? This is again the missing part of the decay curve. Right? There's so little light coming out in that time window that we can't measure it. It's below the noise floor of the detector. So you get prompt emission, which is coming from the axial, decaying. Then we get nothing, because there's no delayed fluorescence. And then we get phosphorescence at the end. Right? And that's the spectrum. Okay? So the axial conformation, especially in axial-axial, is terrible. Really need to avoid it. Then we had real fun because we wanted to measure where the triplets were. So we looked at the phosphorescence of the axial-axial. Right? What we see is that basically we get dual phosphorescence in this system. All right? And this is in Z and X. So what we're seeing is that we get axial phosphorescence grows in earlier times, and then at later times we see the phosphorescence from the equatorial state that's been formed. And the equatorial phosphorescence is a longer lifetime. So we can tell in the axial-axial that even in Z and X we have flipped some. We've managed to turn some in Z and X. So it tells you that in a Z and X host, it's not a rigid host. There's plenty of free volume. It's a polymer. And there's enough free volume for some of the molecules to flip. Right? So the lesson we've learned from that is that Z and X is not a good model for a proper isolated matrix. And that's why we start to see differences in Z and X compared to something like the molecule doped into a typical small molecule host via evaporation. Because then you really are in a rigid matrix. Okay? So you have to be careful with Z and X as well. But you can see that you get this dual phosphorescence. If we then look at what happens when we do this trick with exciting with excess energy. So on the left is excitation at 266, and on the right it's at 355. So you can see at 266, right, what we're actually getting is a lot of acceptor phosphorescence. So it's shifted right over here, and it sits right on top of the phosphorescence band of the acceptor. So if we excite the acceptor, some of the energy is staying on the acceptor. Because when we excite 355, you don't see acceptor emission. So the triplets are decoupled. So the acceptor and the donor triplet are decoupled. They don't talk to each other. This is at much higher energy, the acceptor triplet, than the donor triplet. Right? But it doesn't get quenched. Surely it should energy transfer from the high energy state to the low energy state across the molecule. No, it doesn't, because you're looking at timescales of 50 milliseconds. Right? So that energy is staying there at the higher energy state for 50 milliseconds. So in these molecules, no, not too bad now. I've finished. So in these molecules, I think the thing that we've really got to start to understand, and this is where we need the theorists to help us a lot, is understanding what this orthogonality really means. Okay? So we can have the same orthogonality, so the two donors are parallel with each other and orthogonal to the acceptor. And we can have these systems now where everything is orthogonal to everything else. It's a simple molecule. It's not very big. But just by changing the mixing of the M-pi and the pi-pi states, all right, we're changing the photophysics a huge amount. And when we put energy into one side of the molecule, it does not move. So force to transfer doesn't work on that small distance across the molecule. You're not even Dexter transfer. Right? It sits there. You're doing measurements at millisecond timescales, and the energy's still there, sitting at higher energy. When the low energy state is also there, because we can see the emission from the low energy state as well. So it's not as though they're not there. All right? So there is some really strange things going on in terms of understanding the photophysics. But what we've learned is these conformations do have a big effect. This axial conformation is producing traps and it kills your device performance. Okay. The main bright point about it is the fact that the conformation comes from the fact that the donor has these conformations. So it's the phenothiazine which is introducing the conformations into the DAD molecule. If you use another donor, you won't see this. So what you've got to watch out for is the fact that if you pick a donor and the donor is banana-shaped or something like that, it's got less symmetry, then you might start to get these conformational effects. And you've got to be careful. Okay? So this is fun. I won't say we know all the answers on this yet. All right? But from the naive physics point of view, when I looked at it and said, what's the difference between those two molecules? All right? A few months later, there's a lot of difference between those two molecules. And then we're finding these things out. So, quick question or coffee in question? But I'm